Hello everybody. So welcome back to uh, the second video in the Calculus BC series I'm doing on this channel. So what I'm going to be covering today is the idea of continuity and discontinuity, and essentially what that means. And going forward, that will be a big part of mainly derivatives, but once again, we'll get to that when we get to that. So starting here, I'm covering the idea of partial limits. So from last video, or from the class you've taken, you should be familiar with the idea of a limit. It's what a function approaches when the input variable approaches something. So f of x, when x approaches 2, what are we getting closer and closer to? Now, as I tried to stress in the last video, it's not necessarily what it is equal to, but rather what it approaches. And this is where continuity and discontinuity will start to show. So now we have the idea of partial limits. Well, we know with a limit, as we showed before, it's about what the function approaches from x values. I'm going to use x in this example. X values above and below that specific point. And it's what we're getting closer to from both sides. Now, what partial limits do, and you can see they're essentially the same, only they have this superscript, it's a minus or a plus. It just means we're approaching from one specific direction. If we have this negative superscript or this little minus sign floating up to the top right, that means that we are approaching from x values below. We do not consider anything above, or any x values above the x value of 2 in this case. And when we have that positive superscript, it's the opposite. We're approaching from x values above. We don't care about anything below. So what I'm going to do is I'm going to start with this problem, and we're going to go through these, and then we're going to try this other one. So I want you to think about what these three would be in the context of this one. And you could pause it temporarily, or you can just let it go on. So the first thing I'm going to look at is I'm actually going to look at this last one first. The limit as x approaches 2 of f of x. Well, here is 2. Here's kind of like our important point, and I kind of misjudged the distance here, but get what it's saying. So as we're approaching x equals 2 from both sides, you can see the function just clearly lines up and gets closer and closer to that value of 3. Okay, there's no problems there. Now, that works from both sides. Now, if we look directionally, if we look just from below, well, once again, it's still just approaching that value of 3. It just gets closer and closer and closer. So that would be 3. And the same thing applies for above. We're getting closer and closer and closer, and then we're hitting that value of 3, or rather, we're getting closer to that value of 3. We're not concerned about whether we're actually hitting the value of 3 or not. So these both happen to be the same as that. And that makes sense because in the context of a limit, this is pretty much just both of these put together. So if that's equal to 3, they should both be equal to 3 as well, because this evaluates from both sides. These are just from the individual sides. So after we do that, let's look at this next one. This one here, I have a bit of a messy line going up across because this is just showing where the actual points are. So let's start off with the negative and positive. Not negative and positive, I mean upper and lower limits. So we can see there's clearly something very different about this function compared to this function. It's very messy. It starts out with as a linear function with a positive slope, and then it reaches this point. This open circle means that it's not defined at that point, so it's not actually equal to 4 at 2, and then it jumps straight up to here. This closed circle that I kind of tried to draw in here means that that's what the function is actually valued at, that x equals 2. So it's actually valued to 8, and then it starts as like negative parabola, so it's leading downwards. So if we're looking at x approaches 2 from below, well, we can see we're getting closer and closer to this value of 4. We're getting infinitely closer, and then we're getting ever so slightly nearer to this. Now, the value of f of x at 2 is not equal to 4, but that's not what this is asking. This is asking for a limit. What is kind of, as we get infinitely close, and we're going to be exploring a lot of the concepts of infinitely close and even infinitely far later on in this series, but I just want you to know that it doesn't matter what it's equal to. We can see that it gets closer to 4 at x approaches 2. And from above, well, we have a very different story. We're getting along this parabola, and as we evaluate closer and closer, we see it starts to curve down to this 8. So if I were to ask you, what is the limit as x approaches 2 of this f of x? Well, if we look at them separately, well, it has to be what it approaches from both sides. So as we go from above, it gets close to 8. As we go from below, it gets close to 4. Well, the limit does not exist. This is, we denote with the d and e. It doesn't actually exist. We are approaching two different things from two different sides. The partial limits aren't even equal. So there is no set limit as what the function approaches. You could be like, well, are we approaching from below or above? In the case of a normal limit, it's supposed to be what you're approaching from both sides. So, oh, I did not mean to do that. Well, we're not using that anymore. So that idea is what we're going to be using as we get into the idea of continuity. If you imagine a function, you're generally going to imagine a continuous function. So in general, continuity means that you're kind of keeping something. You're moving along this path without any interruptions or breaks. So in the context of calculus, or just in general mathematics, continuity means that there are no interruptions in the, I could say, quote-unquote, flow of a function. So imagine this here, this one to our left. We can see our function is going, it's increasing normally, and then all of a sudden, there's a break. It's not defined at a, and then it keeps going. Well, it's continuous around here and around here, but it's not continuous at this point a. And the same thing is true here. Even though the function is defined at this point, it's not continuous. There's an actual break in the function here where it just stops suddenly and then it skips to some new value. So these are both examples of functions that are not continuous. Because once again, general continuity, think of continuing. You can continue along your function without any sort of lapses or, for lack of a more official term, any sort of weird spots. So we can see this definitely doesn't make sense. There's a discontinuity here because it's not even defined at that point. So for a function to be continuous at a specific value of x, we're looking at some value a. F of a must exist. So in this case, f of a doesn't exist. So it's definitely not continuous. And it must be equal, f of a must be equal to the limit of f of x as x approaches a. So in this example, f of a does actually exist. It's equal to L. This is what this closed circle shows, but that's not what the limit is. The limit actually does not exist in this problem because they're approaching different things from both sides. So whenever a function is not continuous, that's known as a discontinuity, hence the prefix dis and then continuity. So we're going to look at the three specific types of discontinuities that we cover, and then we'll probably get to some more of the algebraic outlooks on limits in the next video. So discontinuities are areas or points where the function does not continue smoothly. There's a break, there's a jump, there is, in some cases, an asymptote, which you might remember that term from Algebra 2, but we'll get to that after these two. So the first is the idea of a point or removable discontinuity. It's a singular point which there's some sort of break in the function, and I forgot to draw in this. This is important for the other example, this closed circle here. So we see our function continues normally, and then it's not defined there, and then it just continues normally. In this case, it continues normally, then it's not defined where we think it should be along the path, and it just jumps to some other value here. So the function is actually valued at C, even though we can see clearly approaches L from both sides, and then it continues along its way. So the idea of a point or removable discontinuity is that here's the limit. Actually, I can't really write the limit in that, so I'm going to do my best right here. The limit of f of x, so our function, as x approaches a, exists. So I'm going to say it's equal to some L. So it approaches the same thing from above and below, as we can see in both of these examples. Okay, so what makes it discontinuous if the limit exists? Because, yeah, we're approaching the same thing from both sides, but it's not actually what we would expect at that point. So we can see here and here the limit as x approaches a of fx is L for both of these examples. But in this case, it's not actually defined, and in this case, it's defined somewhere else. So this limit is equal to L. In order for it to be a point or removable discontinuity, that has to be true, and f of a is not equal to L. So this is where we get a point or removable discontinuity. If the limit exists, but the actual value at that point is not the limit. We can see here, the limit exists, but the point is undefined, so it's not equal to that. The limit exists here, and the point is defined, but it's not equal to the actual limit. It is down here. And you can see why they call this like a point or removable discontinuity. It's a singular point where there's an issue. You can imagine almost plucking off this little open circle, and the function is continuous then. So that's kind of where the removable concept comes from. Although you obviously can't just pluck it off in real life. It's just a visual thing. So the idea of a jump discontinuity we see is where we have some function, it approaches some value, and then it suddenly just jumps. It jumps to some other value, and the new function might look the same or it might look different, but it starts at some different point. So there's a little just gap here. And how do we know when it's a jump discontinuity? When you look at the actual graph, you can pretty clearly see when it is a jump discontinuity. You can tell that the function jumped. Well, the idea is that the limit of f of x as x approaches a, and we're talking about just being continuous at some arbitrary point a, it's not specific, does not exist. And you can see here why. Because the partial limits, they approach different values. This approaches some value L, this approaches C from below, this approaches, I'm just going to keep using L and C. So the limit does not exist, but I'm going to add the extra stipulation that the partial limits do exist, that they're not equal to each other. So for example, the limit of, you're going to have to pardon the handwriting, the limit of f of x as x approaches a from below, and I'm not even the right end, and the limit, why won't it let me click on this? Okay. And the limit of f of x as x approaches a from above, so once again, the positive superscript. These both exist. You can see it's approaching this value, c, from below, and this value, l, from above, but they're not equal. And that's why this limit does not exist. And I want you to take a moment and look at both the point end removable or the point removable discontinuity and the jump discontinuity and try and figure out why those are the specific stipulations for it. So now we get on to the infinite and asymptotic discontinuity. So what it means to be an asymptote, as you may have learned in Algebra 2 if you took the course, is it's some value for like x or y that the function approaches, like the idea of a limit, but never quite reaches. So if you look here, it's getting closer and closer and closer to this x equals a, I'm going to say, but it'll never reach it. It'll just keep going up faster and faster to infinity, and then it kind of has like a lapse, and then it starts going down from infinity beyond that. And there are algebraic ways to see when this happens, but right now we're just concerned with the idea of the limits. So this happens whenever your limit as x approaches a, either, well, when it does not exist, but in specific situations. When, for example, they both, so if I were to say limit as x approaches a equals infinity. So when we look at the limit and when we say it goes to infinity, we say that the limit does not exist because infinity is not, well, infinity is by definition not a finite number. But another term that they use is the idea that it is unbounded. It has no bound. It'll just keep going forever. Now, if it's unbounded, we can see as the limit as x approaches a, well, technically that is infinity from both sides. The limit from above and below both approaches infinity. So although we say the limit does not exist, the more appropriate term is that the limit is unbounded. It approaches infinity. While in a situation like this, the limit from below approaches, well, negative infinity, and the limit above approaches positive infinity. So once again, this is also asymptotic. And you could also look at, say, from above, it approaches negative infinity, and from below, it approaches positive infinity. So it's the idea of approaching infinity. So the partial limits are any sort of combination of non-finite. So for example, from below and from above, it approaches infinity. You could also have from below, oh, that's the wrong thing. You could also have n from below and from above approaching some negative infinity. You could have from above approaching positive infinity, from below approaching negative infinity. It's the idea that we're going off forever in some direction and we'll never quite reach it. So for this specific situation, f of a does not exist. It will continue to go to some infinite point and it'll never quite reach that value. So f of a does not exist, and our partial limits will go to some infinity, negative infinity, any combination in between. Now, generally, asymptotic discontinuities you will notice because it's usually one of the main reasons why they will pick a specific function. And later on, we'll get to kind of why these things occur or how we can kind of construct these functions that behave in these ways. But for now, I hope most of this makes sense and the idea of limits. If you want to rewatch the first video, that could be good. And we will get into more of the algebraic and slash solving aspects of it later. So hopefully I'll see you in the next video.